Okay, let's dive right into this explainer. We are going to dismantle a 50-year-old sci-fi dream today and replace it with something even wilder. The absolute awe-inspiring reality of deep-time planetary engineering. Look, we all know the trope, right? Humanity travels to Mars, we build some massive machines, and within a few generations, we're walking around outside in t-shirts. But what actually happens when we sit down and run the numbers? Well, in the Red Ribbon, The Long Resurrection of Mars, we're going to find out exactly why transforming our neighboring world is going to be the absolute longest, most grueling story our species has ever told.
So let's start with that classic dream. For decades now, the vision has been beautifully simple. We heat up Mars, we melt its polar ice caps, release a thick blanket of carbon dioxide to trap the sun's heat, and then we just sit back and watch as this rusty, frozen desert slowly blooms with lichen, then grass, and eventually flowing rivers. I mean, it's a completely captivating idea, isn't it? The thought of terraforming an entire planet to be a second Earth is pretty much the ultimate pinnacle of human engineering. But before we go packing our bags for a Martian beach vacation, we really need to hit that dream with some hard, unforgiving data. And this is where a devastating 2023 University of Colorado simulation changed absolutely everything. The researchers asked a really simple question. What if you successfully released every single ounce of frozen CO2 currently trapped in the Martian South Polar ice cap? The answer is pretty bleak. It would only raise the atmospheric pressure to 1.2% of Earth's. 1.2%. That's it. So without a fully pressurized spacesuit, you would still die in seconds. To really understand just how far off the dream is, you have to look at the timeline of what engineers call the classical plan. It is staggeringly long. Phase 1 alone takes a full century just to build city-wide orbital mirrors out in space to focus sunlight and darken the ice with soot. Then you've got 400 years of pumping out super greenhouse gases, followed by 2 millennia, yes, 2,000 years, of deploying cyanobacteria just to turn the rust into dark soil. And by phase 4, taking up to 10,000 years, you finally hit 15% oxygen. But the atmospheric pressure, it would still be a blood-boiling 0.3 atmospheres. You'd need a mechanical counterpressure suit just to keep your body together. You wouldn't look like a settler in a lush garden. You look like an extra in a B-movie sci-fi flick. So that 2023 study, it wasn't just a slight adjustment to the models. It was a brick wall. It marks this exact paradigm shift, where we have to finally leave the optimistic horizon of science fiction and crash headfirst into the uncompromising realities of the spreadsheet. If we are going to talk about Mars seriously today, we absolutely have to talk about it in the after the numbers era. To really grasp why transforming a planet, one that has the landmass of all of Earth's continents combined, by the way, is virtually impossible in the way we've traditionally imagined it, we have to look at 3 insurmountable physical barriers. Now, these aren't just minor engineering hiccups we can innovate our way out of. These are fundamental planetary realities that block the path to a fully terraformed, globally breathable Mars. Let's break these 3 fatal flaws down, one by one. First up is the silent killer. Mars is basically a giant cosmic sieve. Its global magnetic dynamo completely died 3 billion years ago. And without that protective magnetic shield, the solar wind just hammers the planet at 400 kilometers per second, stripping away about 100 grams of gas every single second. And here's the cruel irony. If you try to build a thick atmosphere, it just absorbs more of that solar wind energy, heats up, and escapes even faster. Even if we manage to build an artificial magnetosphere out in space, which would require the output of 1,000 nuclear reactors just to pull off, Mars's low 38% gravity ensures it's always going to leak. It is not a sealed garden. Which leads us perfectly into flaw number 2, atmospheric composition. Here on Earth, our atmosphere relies on a really robust 78% of inert nitrogen. We desperately need this to dilute oxygen so the whole world doesn't constantly catch on fire, and it provides the bulk pressure that actually keeps us alive. Mars, on the other hand, it has almost 0 nitrogen. So that brings us to an absolute inventory nightmare. To replicate Earth's safe pressure over there, we are missing roughly 2,000 trillion tons of nitrogen. Let that number sink in. Where do you even source that? Well, you could try extracting it from the crushing, acidic hellscape of Venus, which, let's be real, might honestly be harder than terraforming Mars, or you haul it from Saturn's moon Titan, where a single cargo run would take a full decade. The cosmic supply chain simply does not add up for a global atmospheric replacement. And if you were holding out hope for some easy fix, 2018 data from the MAVEN spacecraft absolutely crushed it. It measured the remaining carbon dioxide trapped in Martian rock and permafrost. The results? Even if you baked every single rock on the planet and melted every layer of permafrost to release the CO2, you'd yield at most 15 millibars of additional pressure. To put that into perspective, that's the atmospheric equivalent of climbing from the absolute pitch-black bottom of the Mariana Trench all the way up to the peak of Mount Everest. The air would still be completely, hopelessly unbreathable. All right, so the third fatal flaw is the poison right under our boots. Martian soil is heavily laced with perchlorates. These are extremely toxic chlorine salts that severely damage the human thyroid and lungs. And thanks to those massive global dust storms, they literally blanket every dune and crater. To farm or even safely handle the dirt, we would have to physically wash or bioremediate the entire surface area of a planet, equivalent to all of Earth's landmass. So, when you combine a leaky atmosphere, missing nitrogen, and an incredibly toxic soil, you run headfirst into a massive human timescale problem. Look at our history. The Great Pyramid took roughly 20 years to build. The Great Wall of China took about 2,000 years of intermittent work. Terraforming Mars globally, that requires a continuous, highly intelligent, self-repairing effort lasting upwards of 100,000 years. Homo sapiens have only even existed for about 300,000 years. We are talking about committing to a construction project that rivals a third of our entire biological history. So, given the sheer impossibility of the global dream, battling that unbreathable sieve, the lethal soil, and the terrifying risk of a runaway greenhouse effect, turning it into a 150-degree acid rain nightmare, we have to pivot. We need a quieter and, frankly, a much more honest vision. Enter paraterraforming. Instead of trying to magically alter the entire planet all at once, we focus on massive, localized, enclosed spaces. We can actually achieve the atmospheric pressure we need in a time frame that human civilization can realistically comprehend. Think about a feature like Valles Marineris. The scale of this Martian canyon is completely mind-boggling. We're talking 4,000 kilometers long, 200 kilometers wide, and plunging 7 kilometers deep. Now just imagine stretching a massive transparent roof, maybe made of drawn Martian glass, smelted right from the local sand and rock, all the way across that magnificent canyon. And here is the absolute brilliance of the paraterraforming solution. By enclosing a 7-kilometer deep canyon, the sheer weight of the air stacked up to that glass roof naturally compresses down at the bottom. It gives you exactly one full atmosphere of pressure at the canyon floor. Down there, you could actually walk around without a pressure suit. You could plant real forests. The incredibly thick canyon walls would naturally block incoming solar radiation, and the buried ice inside those walls gives you a massive built-in water source. Sure, building one of these colossal canyon domes might take 500 years, but it gives us a true Earth-like sanctuary while leaving the wild, beautiful desert of Mars totally untouched as a planetary park right outside the glass. So stripping away all the sci-fi magic, what does our actual roadmap look like? Well, in the 2040s, we start small, fully pressurized outposts, hidden safely inside underground lava tubes. By the 2100s, we might test some local warming and seed craters with lichens, which, honestly, will probably just die at first. But by the 2500s, we could realistically see a network of domed craters supporting 1 million people. And it wouldn't be until around the year 4000 that a monumental, multi-generational project like roofing Valles Marineris even gets off the ground. But as we look at these vast timelines, we also have to acknowledge a much darker possibility: terraforming Mars accidentally and terribly. Just as we've accidentally altered Earth's climate, we might release super greenhouse gases on Mars without any global consensus, completely overshoot the mark, and end up spending another 1,000 years just trying to cool down a planet we accidentally boiled. The whole question of how long will it take isn't really a specific number. It's more like a terrifying spectrum of failure. Which brings us to the real kicker here. The ultimate realization is this: terraforming Mars is not a technical problem. It is a civilizational problem. Let that sink in for a second. Actually succeeding at this scale requires a totally stable, scientifically focused, and cooperative global government that lasts longer than humans have even been practicing agriculture. It requires a species that doesn't just self-destruct or get bored and lose interest over a span of millennia. And yet, despite all those crushing spreadsheet realities, the massive timelines, and the sheer astronomical costs, we just keep looking up at that red dot in the night sky. Why? Because every single atom of iron oxide on its surface was once born of water-rock chemistry. Billions of years ago, Mars had actual oceans and a sky you could breathe. Trying to bring that back isn't just engineering anymore. It's practically theology. Maybe the very act of trying to resurrect a dead world is exactly what will finally teach humanity the deep time patience we so desperately lack right now. So I'm going to leave you with this final thought to ponder. As we look out at that cold, rusty, absolutely magnificent desert, the question really isn't whether we have the technology to change Mars. The real question is, do we possess the monumental, multi-generational patience required to breathe life back into an entire world? Thank you so much for joining me for this explainer. I hope this shift from sci-fi fantasy to spreadsheet reality gives you a whole new perspective the very next time you look up at the night sky.